This next identity is also known as Pascal's identity. Yes, you heard it right. Pascal's identity. We know that there is one concept that is also similar in finding the coefficients for binomial expansion together with binomial theorem. We call the Pascal's triangle. This Pascal's identity is given here that the n combination of r is equal to, or you can separate them into sums of n minus 1 combination r minus 1 and n minus 1 combination r. So we're going to show that, or manipulate that, this right hand side is just equal to n combination r for this video. So to do that, let's try to start with reviewing what does n combination r means. When you say n combination r, it could be written as n combination r, which corresponds to your n, which means the number of elements in a set, n factorial, over r factorial, the number of elements to be taken from the set of n elements, times n minus r factorial. So we have this formula which will be used later on as well, as we will try to prove this given identity. And by the way, again, this is called to be Pascal's identity. We will be dealing with this again as we move forwards in some topics here in combinatorics. So let's start with this proof. Okay. Again, we'll be manipulating the left-hand side, the right-hand side, because it's more complicated. So you have your n minus 1 r, a combination r minus 1, plus n minus 1 combination r. So for this, let's try to simplify or expand them using this formula separately. Of course, they will be added later on. The first one is, okay, so hopefully you're following. Let me use some space here. We will start with this. For n combination r, which means n is our factorial here, this corresponds to our n. And our r here, this corresponds to our r. So that is what corresponds here in the denominator. So please be guided with that, because as we move here, we will have n minus 1 factorial, because that corresponds to our numerator, as mentioned here, n, all over r factorial, which is just your number of elements taken, r minus 1 factorial, times n here, this your value, minus r, that value. So you have here n minus 1 minus r minus 1 factorial. Okay, that's for the first form. Now for the second, okay, we'll be adding them later, but let's try to look into them one by one. So again, this would be our n. So you will have here n minus 1 factorial, and your r is still r, as similar here and here. So need to worry about that, only that your numerator is different. So you have your r factorial, then you have your times, but your n here again is n minus 1. So you'll have n minus 1. Sorry for this one here. Let me erase some notations. Okay. Now, continuing, minus this value, r factorial. Okay, so hopefully we are following with the expansion. Take note that we are going to add them up. Okay, so let's simplify them step by step, and let me use another color here. So you will have still n minus 1 factorial, let me rewrite it so that you could see this clearly. Sorry for that. N minus 1 factorial over r minus 1 factorial times, removing the grouping symbol here, preceded by negative sign, n minus 1 minus r plus 1. Take note, double negative property, factorial, plus n minus 1 factorial here over r factorial, about this one, so it's just okay, n minus 1 minus r factorial. It's okay to do that because it doesn't have other terms here. Now, moving forward, you have your n minus 1 factorial over r minus 1 factorial. You have minus 1 plus 1, that's 0. You will have your n minus r factorial. Okay, the other one, still n minus 1 factorial over r factorial. What happens to this? I would like to rearrange it, n minus r minus 1, if it's okay with you, so that we can pair it. We have similar forms as this here. Now, take note, our goal is to arrive into this form, but this is still two terms. So we can now combine them into one expression. But of course, we will talk about our LCDs before we can actually look into the correct forms to be combined. Now, I would like you to take your attention to this portion here. Now, r factorial is again r times r, that's r minus 1, r minus 2, until 2 times 1. But r factorial could also be written as r, and the combination of all of this is actually just equal to r minus 1 factorial. Okay? Because if we have to multiply all of this, starting with that, it follows the same idea of n factorial be n times n minus 1 until 2 times 1. It's just that it doesn't start with n, nor here it doesn't start with r, but it starts with r minus 1. Hence, it's again r times the combination of all of this, which is actually equal to r minus 1. That is the reason why the reason for that is on our denominators you have r minus 1 factorial, but we don't have here. But you can express this in this form so that you will have r minus 1 factorial. Okay? So that's the one thing, but we are not yet done. Hopefully that's clear, because the second item I would like you to know is actually this item here. Okay? So following this idea, if you have n minus r factorial, that means it follows this form. N minus r times n minus r minus 1 times n minus r minus 2 until 2 times 1. Similar to what happened earlier, if I have something like this, I can rewrite n minus r factorial just as the product of n minus r, that's r, and the combination of all of the products of this. Similar earlier, the combination of all, starting with r minus 1, is r minus 1 factorial. So since it starts with this, that's actually equal to n minus r minus 1 factorial. Hopefully this is clear, because aside from this two earlier, this form and that corresponds to something like this. So breaking those parts, okay, I would like to break all those parts for you to easily see them. N minus 1 factorial times r factorial is still r minus 1 factorial rather, but n minus r factorial, let me rewrite it in this form. Okay, that's actually n minus r times n minus r minus 1 factorial. Okay, so that's the same here. I don't have much space. Hopefully you'll bear with me. Plus n minus 1 factorial over. Now let me break this into this form. R times r minus 1 factorial. R times r minus 1 factorial times this as it is, n minus r minus 1 factorial. We did this because for LCD, we know that coming up with LCD, we need to look at the factors of our denominators. You have r plus 1, r plus 1. That would mean in our LCD, we still have r minus 1 factorial, right? That's part of the LCD. Then, you have n minus r, as I forgot r, so r is here, n minus r, so n minus r, and then you have this as part of your factor, n minus r minus 1 factorial. So all of them are factors needed for our LCD, because if you have, say for example, 1/8 and plus 1 over 12, you need to look for the factors of 8. We know that 8 is 4 times 2, and then your 1/12 is 4 times 3. That's why your LCD for this is actually 4 times 3 times 2, 4, 3, and 2. Similar to this, you have these factors, all of that in general. I might be using a separate page for this, so please bear with me, because as I need to look into the sum of the two rational expressions, we know that in LCD, we use this, divide with this term, what remains, multiply it to our numerator. So this 4 to be divided by this 3, so cancel n minus r, cancel that. What remains is r That is what we need to multiply for our numerator, which is n minus 1 factorial. So you have here r times n minus 1 factorial plus, for the second second rational expression, all of this to be divided with this form. So you have r minus 1 factorial, n minus r minus 1 factorial. What remains is this. That will be multiplied to our numerator, which is n minus 1 factorial. Okay, so please bear with me. Hopefully you're following with that concept. So you have here again n minus r times n plus 1. Sorry, n minus 1. My bad. N minus 1 factorial. So please bear with me as I mentioned. Let me move this on the next page. Add page. Okay, as we add a page. So let's paste it here. Paste. Okay. So for those who forgot, take note that this is, let me move it again. Okay, move it again here. Because this is just equal to this form here. Let me copy that so that we will not be forgetting that. Combination of n minus 1, r minus 1, plus n minus 1 combination r. This is equivalence. And take note that what we're trying to show is this would yield to n combination r, which is equal to this form here. You have n factorial over, r factorial n minus r factorial. Okay, this is our goal. So let's continue with this. So equal to, now look at what happened to our numerator. We have common n minus 1 factorial. So let's factor that. So you have your n minus 1 factorial. What remains here would be r plus n minus r, right? Sorry, no factorial by the way. Okay. As we factor this, you have r, that's correct. Factor that, you have n plus n minus r. All over. Now look at our denominator. If we pair these two, and this was part of our discussion earlier, if we're going to return to this page, the combination of the two, r times r minus 1 factorial, is just r factorial itself. So again, the combination of these two is just equal to r factorial itself. Now, similarly, for these two remaining two terms in our denominator, n minus r times n minus r minus 1 factorial, is actually also explained here earlier. N minus r, this one here, times n minus r minus 1 factorial is the n minus r factorial. So going back here, this is again n minus r factorial. See that our denominator already matches our target. So we just need to finish our numerator. That's actually n minus 1 factorial times, if you're going to remove this grouping symbol r, plus n minus r. You know what happens to these two, right? Let's do that later. Over r factorial times n minus r factorial. As mentioned, r minus r is 0. So you'll have here n minus 1 factorial times n over r factorial and n minus r factorial. If we're going to interchange the terms of your numerator, you'll have n times n minus 1 factorial over r factorial times n minus r factorial. And please be guided, our goal is our numerator to be n factorial, is the product of these two, n factorial. Now going back to our previous page, we already introduced that here. This one. If we're going to have all of this similar to what happens to r factorial, that's n times n minus 1 factorial. Because n minus 1 is what is the first term in that string of terms to be multiplied. So again, going back here, this is just equal to, the product of these two is just n factorial over r factorial times n minus r factorial, which is our intended target. Okay? So just to finish this, we know again this is actually n minus 1 combination r minus 1 plus n minus 1 combination r equal to n factorial over r factorial minus n minus r factorial, which is equal to the combination or n combination r. Hence, you simply finish it here. We can use symmetric property. N combination r is equal to n minus 1 combination r minus 1 plus n minus 1 combination r. So we are done with the proof for the Pascal's identity. Yes, it's very long because we need to look into the additional processes, and we are proving here algebraically. Okay, there are also proof using combinatorial proof, but this is just a proof using algebraic methods. So we have shown this to be true, and for some instances later on this may be used, so please bear that in mind. Thank you very much for watching.